All right, today we are looking at the last bit of this integral calculus. And so lengths of curves. So there's an explanation if you are interested. In your text, page 356. But essentially, if we have a curve of some sort and we want to know the length of the curve between x equals a and x equals b, so this length in here. Alright, so this, I want to know how long that is there. Basically, if you break it up into bits of straight lines and then you put more straight lines in there, you can then use calculus to help you out. So, what you get then is this. So the length of the curve y equals fx. So it's fx is that function, and the length of the curve is the red bit. From x equals a to x equals b is given by L equals. Alright, so as I said, essentially what we do, just run that again, essentially what we do is we do some straight lines, find the length of those straight lines. We can find the lengths of those straight lines easy enough. And if we know the coordinates of those points, and then we can find them, and then we can put more, and the more straight lines we put in there, the closer that length becomes to the curve, which then, similar to the area kind of thought process, that then becomes, when you add all those things up, similar to what we talked about again with the volumes of revolution. That's the one I was thinking of. Volumes of revolution. So it's 1 plus the derivative of our function squared dx. And so essentially this bit is like, well, if you want to know the length of that, if you know those two sides, the x and the y, if you know those bits, you can use Pythagoras. Alright, for that length, that's where the square root of this square plus this square, essentially, is what that is. Alright, so that's the equation that we use to find the length of this curve. Alright, so there's more information in your textbook about all of that if you want to have a look. It's also, I'm pretty sure it's on your formula sheet as well. Just down next to the, or underneath the volume of revolution one. Alright, so let's do an example. So,
sorry. I got Sally set up. Really enjoy that.
Alright, so we've got this curve, its functions 3 over 2, x to the 3 over 2 I should say, and we're looking between 1 and 4. Alright, so a is 1, b is 4, between 1 and 4, 1 and 4, and the function there, x to the 3 over 2, and so we're after how long is that. Alright, so when we look at the formula that we've got to use, we'll notice that the derivative of the function is here. So first of all we need to put that in. Alright, so the derivative f dashed x, polynomial, power comes down, x to the power of half. Alright, so we've got that. So, but when we put it in, we need to square it. So f dashed x squared is 3 over 2 x to the half, and then we square it, which becomes 3 over 2 becomes 9 over 4 x to the half. What do we do with these indexes? Times them, yeah. So it's x to the 1. Alright.
Oh, it's also a square root, and a square root times square roots.
Okay.
The x to a half
Yes.
is the square root of x.
Times the square root of x times the square root of x is just x, yep. Either way of thinking about it, it brings you to the same conclusion. So then, our length would be, according to the length formula, from 1 to 4. Right, so these are our A and our B. From 1 to 4 of the square root of 1 plus function of x squared, we've already got that, 9 over 4x and dx. Alright, so we can do some stuff with this to simplify what's inside that square root. So if I put them over a common denominator of 4, I've then got 4 plus 9x over 4.
Why is it the integral 1 to 1 now?
Because I didn't write the correct number there. That would be why. Alright, so then this 4 down the bottom here, I can bring that out. And when I bring it out, it becomes a half, yeah. And that half, because it's a constant, I can stick it right out in front of my Alright. Now, what are we going to do? Got to anti-differentiate this. What technique are we going to use? Because we've got a function inside another function. U? Yep, let U. So whenever you have a function inside another function, first thing you think about is if I let U equal something. Of course, if that was 1 over, you would think...
It's a sine.
Yeah, inverse circular. All right, so what are we going to let U equal?
Would you let U equal 9x or 4 plus?
4 plus, the whole lot.
Yeah.
a whole lot because this bit becomes u to the half, doesn't it?
Yeah.
Alright, so du dx is? 9, yep. And then this dx, we've got to replace that, so that's going to be replaced with du over 9. And what else are we going to replace? Going to replace our limits on our integral, because now we're going to change this, our variable, from x to u. So we need u's up here, u values up there. So when x is equal to 1, u would be equal to 4 plus 9 times 1, which I think should be 13. And when x is equal to 4, u would be 4 plus 9 times 4, which is 36 plus 4, 40, I hope. Alright. So, let's stick that in there. Let's see what we get. So now we've got that our length, that half is still there, that doesn't go anywhere. Alright, that stays there. And now I'm going to change to u, so 13 to 40 of u to the half, and dx is du on 9. That 9 can come out here with the half. And when we anti-differentiate u to the half, what do we get? Anti-differentiation, we
3 over 3.
increase, so 1.5, 3 over 2. And what do? Divide it by 3 over 2. We're dividing by a fraction, so we flip it, multiply. So 2/3 times, if you like. Alright, what do we do now? Stick in the numbers. Alright, put 40 in. 2/3 of 40 to the 3 over 2 minus 2/3 times 13 to the 3 over 2. See what I've done in the notes, whether I've done it exact values or I've cheated. Oh yeah, yep, there's some interesting stuff there that I've done. Alright, so first of all, because you've got 2/3 there, it's effectively now common factor, yes? Yeah, we can put it out here with that. And so, 2 1s are 2, 3 18s are 36 plus 18 is 54. Which of course that's 1/27. And now we've got 40 to the 3 over 2 minus 13 to the 3 over 2, which apparently, because I've prepared one earlier, (40 to the 3 over 2 becomes 80 root 10, and 13 to the 3 over 2 becomes 13 root 13. So that's for a bit of fun. No? Alright, now, just notice.
Expand that.
Hey?
To expand that.
Could you expand it? 6 of one, a half dozen of the other, isn't it? Could.
Leave it as that.
I'll leave it as that. I mean, there's a whole bunch of different variations, isn't there? That you could put that, whether any of them's going to be any better than that or not. All right, anything about that I did? No? Nothing at the moment. All right, so I've got in my notes that your calculator can do it. So according to the calculator, have it set in, it's in the main menu, have it set in standard and rad. Ah, thank you. It's all right, people in YouTube land can't see it anyway, but I guess you want to. All right, so according to this, if we go main, interactive, calculation, line, so calculating something about a line, what are we, we're arc len. So let's write those down here. What we're doing, so on our calculator, so calc, on our main screen, we went interactive, then from interactive we want to do a calculation. What do we want to calculate? We want to calculate something about a line. And what is it about the line that we want? We want the arc length. So ARCLEN. And so when we click on that, we get a box. And so the expression, all right, so the expression we used, I've rubbed it off now, but that was the expression was x to the 3 over 2 that we worked with. The variable is x. Then where do we want to start and where do we want to end? Well, we wanted to go, for our start, we wanted to start at 1, and the end, we wanted to end at 4. So if we put those things in, x to the power of 3 over 2, start at 1, end at 4, okay, and so there it is, which is the same as what I've got. Hey, winner. All right, anything about that? No? All right. So there is a version of the formula, the length formula that we've done, which I've now rubbed off, for parametric equations. So that's when you have your function rather than fx, or y equals something in terms of x, you've got x and y in terms of another parameter, say t for example. And so the length of a parametric curve, not much space between, of a parametric curve so there's some similarities. Length is L, still from A to B, we've still got the square root. Instead of dx, we have dt, which is our parameter. And this inside here still looks similar, but not quite exactly the same, but similar. So in the first bit we have dx dt, and in the second bit dy dt. So effectively, it's saying how much does your x change by, how much does your y change by. Use Pythagoras to find that length. And there's more in your textbook, page 358. All right, better do an example, eh? Example. Okay, so one other thing I'll point out. So in the previous version, because it was dx, these were x values. But now, because this is dt, our limits always in terms of what our variable is. So this is t equals a to t equals b. And that's what we've been given here for our domain of t. All right. So the formula, there it is, L equals. So we've gone from 0 to 2 pi for t, square root of. All right. dx dt, I probably should have done those first before I wrote that up, shouldn't I? All right. So what is dx dt? Negative sine t, and dy dt, cos t. Alright, so put that one in there, put that one in there. Square root of negative sine t squared plus cos t squared alright, sine t squared is negative sine t all squared is sine t squared. Right, be careful, it's not just the t that's squared, it's the sine of t that's squared, so it goes here. Same with the cos, it's not the t that's squared, it's the cos of t that then gets squared. Alright, and sine squared plus cos squared is? Yep. So integral from 0 to 2 pi of the square root of 1 dt can be simplified further to 1, yep. When we anti-differentiate 1, we get, yep, but in this case, the variable we're using is t, so we get t. 2 pi to 0, and let's squeeze the answer in here, 2 pi minus 0, which is, whoops, 2 pi. Just notice my notes have got a mistake there. Fix that up. My notes are x, not t. So remember, the variable's t's. Right. Anything there that you want me to clarify? No. All right. 8E.